So, now let us go to the second part of the isomerism, that is stereoisomerism. Stereoisomerism. In the stereoisomerism, as I said, there are three parts are there: conformational isomerism, geometric isomerism, and the optical isomerism. The first we will take a conformational isomerism. Conformational isomerism. The requirement for this isomerism, when you will get a conformational isomerism, the first condition is that there should be two carbons attached with a sigma bond. A sigma bond should persist between the two carbons. That means one carbon compounds, like example methane and CCl4, these compounds will become not eligible to show this isomerism. There should be a CC sigma bond. So, one carbon compounds and two carbons containing double bonds like ethylene also not eligible to show this conformational isomerism. And second eligibility is not only sigma bond, but there should be some groups should be there, like some groups, some A, B, C, or all A, I do not have any problem, but some groups should be there. The groups means not necessarily functional groups. You can have the minimum is hydrogens, all hydrogens. Okay, fine. This is eligible, all hydrogen. This side 3, that side 3. So, both the sides, some groups should be existing like a minimum hydrogen. If some groups are chlorine, some methyl, it's well and the discussion, it's excellent. But the compounds like single bond is there, but attached with a triple bond like this, not possible. So, there is a sigma single bond is there, but the groups are not there. So, this will become a not possible. That cannot show any conformational isomerism. So, these are the two fundamental requirements. There should be a carbon-carbon sigma bond. That sigma bond attached carbon should have some groups and both the carbon should be sp2 sp3 hybridized carbons. Then only you have this type of the some hydrogens or methyl, chlorine, some groups will be possible. Then the carbon is and the carbon bond is believed to have certain two properties, like for example, if the two pieces, wooden pieces are attached with a nail and fixed the other side and twisted the other way like this, then the two pieces are allowed to rotate like this. Between the two pieces I have an iron nail. This will have the two qualities. One is the nail is very strong, you cannot break it, it is very strong. Like that, my carbon-carbon bond between the two methyl groups also is very strong. So, one quality of the CC bond is it is very strong bond, not easy bond, like an oxygen-oxygen or a nitrogen and nitrogen single bond. They are liable to break up, but the carbon-carbon bond is one of the strong bond. Second one is just like a nail, it is twisted the other side, but the hole is little big so that you can freely rotate. So, you have a free rotation, isn't it? Free rotation means not having any problem, isn't it? Free rotation is there. So, it is strong enough, but free rotation is there. So, these are the two qualities I have. So, two wooden pieces can be arranged like this, so the two car wheels are arranged through an axis. They cannot go individually this side and that side. They are tied up, but they are easy to rotate. Both can be same side, opposite side, one this side, one other side. So, free rotation is there without any problem, but at the same time the bond between the carbon and carbon is very strong. So, the carbon and carbon has two these qualities which are in fact contradicting to each other. Generally, when a rotation is free, we try to pull it out, but it won't come, it is very strong bond, right. Because of these two qualities, we are going to observe certain phenomena here. So, the best example for this conformational isomerism is ethane. It is small also, However, it is very simple to understand. Now here onwards, to understand all this stereoisomerism, we should also have some knowledge of the how a three-dimensional molecule is written on this board is a two-dimensional one, and I am going to write a three-dimensional one. This has got a different methods. One such method is seeing the molecule from the front view. That is called a Fisher model. That is called a Newman model. Newman model. In this model, this ethane molecule is written as carbon. I am writing 3 sides, 3 hydrogens, which are shown towards you, and the carbon is there. All the hydrogens are projected towards you, and behind the carbon there is one more carbon, but that carbon is backside this imaginary disk. There is another carbon behind this carbon. What is this circle? The circle is an imaginary disk separating the carbon 1 and the carbon. This is carbon 1, this is carbon. An imaginary disk I am writing. Behind the carbon 1 there is another carbon, which is also having the 3 more hydrogens, exactly backside only. But if I don't write, people think there is nothing. So therefore I write that hydrogens also, but don't make any angle. They are parallel to the first lines and touches another carbon. So how many carbons are visible now? Means only 1, because first carbon is visible, second carbon is behind the first carbon. So 3 hydrogens are attached to the first carbon, another set of 3 hydrogens are attached to the second carbon. So this is just like a horse is coming towards you, you are looking from the front side. So this Newman model itself is called front view. Imagine there is a horse coming towards you, you are looking from the front view. You cannot see the tail and back legs, but I am somehow writing this just like side by I am writing. Okay, strictly speaking, the first 3 will cover the second 3, but in order to show their presence, I am writing, if possible, little small size, because they are little far away to me. The 3 hydrogens are projected towards you, the other 3 hydrogens are projected backside. They are not straight like this, they are projected towards you. The other 3 are projected towards you, but from long distance they appear just like they are standing projecting upwards. No, they are projected towards you, isn't it? In order to see the angle, it is 109 degrees 28 minutes, right? Now this is called one ethane molecule. As I said, between the 2 carbon the bond is rotatable. So either the first one or second one, keep it constant, rotate the second one, right? First one is constant, right? But the second one I rotated. So all the 3 hydrogens are attached to the second carbon, all will rotate. So writing the second set of hydrogens only up to the disk, they are imagining that they touch the second carbon, right? So this is also ethane. So if when you burn, both will give 2 moles of carbon dioxide, 3 moles of H2O, right? But the distance between the 2 hydrogens, between the 2 and between the 2, if you measure, there is a less distance between 2 hydrogens, A and B hydrogens. If you take between 2 hydrogens, less distance. Observe this clearly. The distance between the hydrogens are like this. When I rotate like this, it is gone the other side. So therefore what we get is more distance. More the distance, less will be the repulsion. Less will be the repulsion. When repulsion is less, stability will be more stability will be there. When stability is more, its potential energy will be less potential energy. The energy associated with the molecule is called potential energy. The molecule will try to occupy at a lower potential energy state. When both the molecules, when you burn it, both gives carbon dioxide, water, but this potential energy is less, therefore it liberates less amount of energy. that is called heat of combustion. So this molecule will therefore will have a less heat of combustion. Heat of combustion. Combustion means what? When the molecule bond into carbon dioxide and water, the energy liberated per mole is called heat of combustion. So both gives carbon dioxide and H2O, same moles and all that, but a small quantity of heat will be less liberated, more liberated. That is enough to identify them as a different compounds, or to call them as isomers. What isomers means? By rotation they are exchangeable. They are exchangeable. Okay? By rotation. That rotation of CC bond, we call it as a conformation. Conformation means rotation of CC bond. So these two are called, therefore, compound A and B are nothing but the same compounds, ethane and ethane. Okay? Let us call this ethane with a small prefix, syn-ethane and anti-ethane. Both are ethanes only. What is anti? Anti refers to opposite. What are opposite? The two hydrogens, you see, there is a first carbon, one hydrogen, second carbon, one more hydrogen is opposite. Here no such opposite arrangement, same side, same side, same side. Here opposite arrangements are there. That opposite arrangement reflecting in its name anti. Anti means against or opposite. So in the anti-ethane, the hydrogens, these two are opposite, these two. All the 6 hydrogens are arranged in opposite manner. So therefore repulsions will be less, leading to give stability, more stability, less potential energy. So some energy will be less when you burn such a compound. So therefore one is giving less heat of combustion, one is giving more heat of combustion. That's enough to recognize them as a isomers. So however, these two compounds, just like in the structural isomerism, there is an equilibrium, right? Those are called what? Tautomers are equilibrium. Positional, functional, chain, all are not interconvertible unless you break the bond and make the other compound. That's not possible to convert. But here we said that already one type of isomers in the tautomerism are interconvertible. Here also they are also interconvertible. They are very easy because just rotating the single bond we are interconvertible. So the energy required is very, very small. For this you need not to heat it or do anything. The energy which is there in the surrounding enough, that is at room temperature we have 25 degrees centigrade availability of temperature, that's enough to promote. However, if you go to the Kelvin 0, all the motions will be stopped. In such a condition, A cannot be converted into B, however. But at room temperature, the A and B are interconvertible. Out of that, which is more stable? B. So which percentage will be more? Always B. At any temperature, B percentage will be more. But as the temperature increases, the relative ratio will be decreases. As the temperature increases, the ratio, relative difference will be decreases. As the temperature goes down, A percentage will be less, B percentage will be more. So once it goes to the B, B may not come back. As the temperature decreases, when you go to the minus, the A percentage will be less and B percentage will be more. But when you come to the higher temperatures, there is no much difference between A, B, but always at all the temperatures B percentage will be always dominating. Such a stable conformer we also called staggered conformer. Staggered means opposite conformation, or you too can say another meaning, that is more stable one. Staggered conformer. Conformer means conformational isomers are called conformers. By rotation you are getting, therefore they are also called rotamers or conformers. If all are hydrogens, we get only two. One is syn, one is anti. After every 60 degrees, if you go on start rotating like this, 60 degrees you get this one. Again 60 you will get back the A. So A, AB, AB, AB. So you go on rotate to 180, 360 degrees. You find A after B, after again A, again B only. So two conformers only you are able to get. In between let us say after 10 degrees what comes? You may recognize them all between are called Gaussian conformers. You can call as a Gaussian conformers. But let us take some bigger molecule. To study further, you can take a molecule like N-butane. N-butane you can take and discuss the different types of the conformation. So let us, we are taking the rotations of between the second and the third carbon, we are rotating. Now these two carbons are taken as a ethane, right? So first carbon is this one, behind there is one more carbon, but this carbon is taken, this is second carbon, right? 1, 2, so this is second carbon. The second carbon has how many hydrogens? 2 hydrogens, so 2 hydrogens. And second carbon is attached to one methyl group, so let us write methyl here. So first carbon is methyl, second carbon is this one, second is attached to the third carbon, so second carbon, behind the second carbon there is a third carbon which is also attached with once again one methyl group and 2 hydrogens. So now read the carbon 1, carbon 1 is methyl, carbon 2 is front carbon, carbon 3 is back side the second carbon, right? So carbon 4 is methyl, so this is the methyl. So this you call it as a syn N-butane. So where 2 methyls are exactly overlapping, actually strictly speaking, their first methyl covers exactly second one, but for the sake of studying I have written slightly side by. Now the you rotate the 60 degrees between the second carbon and third carbon, you are rotating. So keeping the first carbon methyl as it is. So this methyl is as it is, but the second, third carbon axis I rotated. Carbon you need not to write that. So the methyl group comes opposite to this. So therefore one methyl has come here. There is one hydrogen, there is one hydrogen. Okay. So this is 60 degrees rotation. This rotation is called a torsional angle is rotated, or between the methyl and methyl the angle is not bond angle, it is called torsional angle, or it is shown with 0. Theta is equals to 0 degrees. Between the two methyls what is the angle means? Not bond angle, that is called torsional angle or theta, okay, or dihedral angle, because two tetrahedrons are there, taken grand they are coming into the same plane and then taken this measured. So the angle is not bond angle, once again it is torsional angle between these two is theta is equals to 60 degrees. Okay. Then once again rotate one more 60 plus one more 60 means total 120. From here to here 120 degrees if you rotate, you will get the first methyl will be as it is, right, and second methyl will come behind the first hydrogen, right. So the another hydrogen here. So this is your methyl. Methyl has come to back side of the hydrogen. The methyl has come back side to this hydrogen. Still rotate one more 60. Total is 180 degrees. Then the first methyl will be upside. Second methyl will be opposite to the first methyl. Opposite. The rest are the hydrogens. The one more 60, that is 240 degrees if I rotate. Then first methyl always keep it as a standard. Second methyl comes behind this hydrogen. Rotate one more 60, that is 300 degrees. So you will get the first methyl as a standard, top one. Second methyl will be opposite to this hydrogen. And 360 degrees if you rotate, you will get back the original one. So there are 6 conformers are coming. Let us say 1, 2, 3, 4th one, 5th one, and the 6th one. The first one is called syn N-butane, and opposite one, two methyls exactly opposite one is called what? Anti. The sixth one is called anti-N-butane. Now the methyls separated by right side 60, left side 60. Both are called now Gaussian conformers. Gaussian 1, Gaussian 2. Where one methyl and hydrogen, methyl hydrogen, two times it is overlapping, isn't it? In this case also methyl hydrogen, methyl hydrogen. This overlapping situation is called eclipse conformer. Eclipse 1, eclipse 2. Now read the order. Syn-butane, Gaussian 1, eclipse 1, anti, eclipse 2, Gaussian 2, coming back to the syn conformer. And out of that, which will be the most stable? Anti-conformer. So stability order will be the order of stability. Anti will be the most stable one, and syn will be the least stable one. Syn will be the, because more overcrowding, more the crowding, more repulsion, potential energy very high. So stability will be less. This is stability order, right? It is stability order. So the most stable one is anti. Least stable is in between these Gaussians. Two Gaussians are identical, almost left side, right side. Two eclipses are identical. But out of Gaussian and eclipse, each one has one better point. They are separated here, one point. Therefore, repulsion will be less. Here, they are separated much more, so better point. But hydrogen methyl is crowded. So therefore, they have one minus point. What is that? Crowding, methyl and hydrogen. But two methyls separation is here, 120 separation, 60 separation. So each one has got one plus point. More separation, but crowded with hydrogen. So therefore, the eclipse has one plus point, one minus point. That's why the first comes Gaussian. So therefore, after anti, Gaussian 1 is equals to the Gaussian 2, more stable than the eclipse 1 equals to the eclipse 2, then the syn comes. So angle of separation, if you see, anti will have a 180 separation. So more the separation, more the angle of separation, more will be the stable. Syn angle of separation is 0 degrees. Syn will have a theta 0. So the 180 comes first, 0 comes later. But here eclipse is 120, Gaussian is 60. First 60 comes, then 120 comes. So it is 180 means 120 should come here. So remember, 180 followed by 60, 120 and 0. So it is the groups, more the separation, more will be the stability. In the anti, we have a all opposite, isn't it? This is looks like a anti-ethane, and also the two big groups are opposite. So here also opposite, but two big groups are not opposite. Methyl hydrogen opposite, methyl hydrogen opposite. Two methyls are almost very closer. So this and this you compare, both are anti-conformers, but two methyls are opposite, two methyls are close here. So there, out of these two, this is more stable. Out of these two, this is more stable. These two are less stable, these two are more stable. So out of this pattern of arrangement, in between arrangement, when you put a flower vase, see that the no two flowers are touching and equally balanced also. Two big flowers, when you put one for the east side, one for the west side, like that, two big groups are opposite will give the more stability. That means the interruption or the repulsion between the, because of the size more, the bigger size more repulsion. Two bigs are opposite, so maximum stability for the anti. This is called here staggered conformer. Write the staggered conformer of the N-butane, means you have to write this one. One methyl up, one methyl down. The other groups are written like this. Instead of here, now this molecule is very close to the two carbons with two chlorines. Rest are hydrogens you can take. Okay, two chlorines containing ethylene, two phenyls containing ethane, right? This is 1,2-diphenyl ethane, 1,2-dichloro, dibromo, okay, diethyl, so on. So, this bond go on rotating, you will get the 6 conformers, of which order will be the anti-most stable, after that Gaussian, after that eclipse, then comes the sin, the order, relativity and so on. If the compound is complicated, for example like this, if this compound is there, I am rotating this bond, okay, and now let us take, this is the first carbon, this is second carbon. My first carbon has one ethyl group, one hydrogen and hydrogen. So, I must write like this, one ethyl. So, let us put C2H5, okay, and hydrogen and hydrogen. And this carbon has 2 methyls and 1 hydrogen, right. So, 2 methyl groups and 1 hydrogen means 1 methyl, 1 methyl, 1 hydrogen, like this. Now, these two are nothing but the same compounds. I am rotating between these 2 carbons, taken as the first carbon, taken as second carbon. This group is the ethyl, this is the methyl, this is the methyl and ethyl. So, now these 2 compounds are nothing but this is the one of the conformation structure of this compound. Instead of 1 methyl, if I put ethyl, the formula will have 1 more carbon extra. So, this is no more a conformer of that one. I can rotate this one and write, this one I rotate, this one I rotate and write the conformational isomers. But for a given compound like N-butane or dichloro, diphenyl, better rotate the center carbon and get all meaningful conformers, that is syn, Gaussian, eclipse and the anti-conformers, in which anti-conformer will be the most stable one, right. Except a few cases, like for example, I will give one specific example, a CH2 with OH and OH. In this case, it seems to be a OH of the first carbon OH, and the second carbon OH will have a hydrogen bonding, it seems. This is called what? A ethylene glycol. We expect the anti-conformer will be the most stable. But in this particular case, ethylene glycol, Gaussian conformer. Gaussian means what? First group, second group separated by 60 degrees has got an intermolecular hydrogen bonding, and the Gaussian conformer happens to be the most stable or staggered conformer of that particular series. But otherwise, in general, the 2 big groups opposite, 2 phenyls opposite, 2 chloro opposite, such conformers will be the most stable.